So what we're going to do today is we're going to talk about benefits of concurrency, and this will then help to give you a bigger picture view that should make it easier to implement assignment number 3. So we're going to talk about the motivations for and benefits of developing concurrent software in general, and then of course we're going to specifically focus on Android. Although you'll see that there's a lot of discussion here that's applicable to programming in C# or programming in C++ or programming in C, or Java for that matter, although our specific examples will focus on Android features. So why would you want to use concurrency? You'll soon discover as you start to play around with it that concurrency is a double-edged sword. It's got a lot of benefits, but it also comes with some costs, where the costs are basically the complexity of figuring out how to make it work and debugging how it works when you start using concurrency in your programs. So it's kind of important to think about what's the reason for this. Why should you go through this pain? And there's a bunch of different reasons. One reason for using concurrency is to leverage all the advances in hardware and software that have occurred over the past several decades. And this is leading to what we sometimes call commoditization. Does anybody know why I have a picture of coffee beans when I mentioned commoditization? It's a commodity, right? So what are other examples of commodities besides coffee? Yeah, so grains, arguably oil, depends on a variety of different factors. Pork bellies, if you watch the movie, what is it? Trading Places, orange juice futures, all this kind of good stuff, right? So you can go and look at this link to find out more about commoditization. There's a great quote in this article I wrote many years ago where John Chambers, who is the CEO of Cisco and has been for a long time, says, in the world of today and the future, everything gets cheaper forever. That's his definition of commoditization. And while that's certainly true of hardware, it's certainly true of software, it's probably not true for housing prices in California, right? So they don't get cheaper forever. Other things get cheaper forever, but not everything, because it's not a commodity, right? So here are a couple advances that make commoditization of hardware, and we'll talk later about things that are making the commoditization of software. So the most famous thing that makes the commoditization of hardware is something called Moore's Law. Does anybody know what Moore's Law basically says? Yeah? Good. So the definition, which you can read about here, is basically the number of transistors in an integrated circuit doubles every 2 years-ish. So 18 months, 2 years, 3 years, sometime in that time frame. And this has been going on for a very, very long time. We'll talk in a second about what Moore's Law doesn't mean. People used to think it meant something else, but it means that the number of transistors keeps going up. So in a nutshell, people are able to pack more and more onto the same amount of space. Or another way to look at it, you can pack the same amount of stuff into smaller space, or you can pack more stuff into the same space. Now, one of the other things that's happening, and we'll see why this is happening in a second, in addition to Moore's Law, is a big movement towards so-called multi-core processors. Anybody know what a multi-core processor is? When?
Processor, it's like multiple processors that can easily.
So in a sense, it's a single processing component, like a chip or a chipset, that contains 2 or more CPUs that can read and execute instructions, program instructions, in parallel. So that's basically what a multi-core processor is. Now, why has that become so popular and important? Does anybody know why multi-core is taking over the world? So something very important has happened. Yeah, when?
It's very difficult to continue sustaining Moore's Law.
It's difficult to what?
Very difficult to continue sustaining Moore's Law.
So Moore's Law is going quite well. But what Moore's Law just says is the number of transistors on a chip keeps going up and up. So that is indeed the case. What Moore's Law doesn't say is,
Like the heat generating is too crazy.
so power and heat is one thing.
Just the frequency, going off the power and heat, the frequency has reached a point where an increase in frequency kind of has a much larger increase in power consumption.
Right. So another way to look at this is that clock speeds have leveled out. Even though we still have lots and lots of transistors, the ability to run these things faster and faster, which used to be almost synonymous with Moore's Law, has kind of reached a plateau. And this happened about 10 years ago or so. So for a while, clock speeds kept doubling every 2 2 years or 24 months-ish or so. And that was cool because it meant that people could keep the same piece of code, and if they went to the beach for 2 years and came back, the code would run twice as fast. But with the clock speeds not keeping up with the transistor density, all of a sudden that wasn't happening, and so everybody started to freak out. Yeah?
So isn't a CPU like a processor?
A CPU is indeed like a processor. In fact, it's so much like a processor, it's its middle name, CPU.
What's a single processor containing 2+ processors?
So they're cores, right? They're processing cores. Yeah?
What's limiting the clock speed?
Heat, largely. So that goes back to the power and the heat and stuff like that. So the problem is that the clock speeds haven't kept up with the ability to have transistors. So if you read this article, it goes into this much more detail. It's called it says, the name of this article is No More Free Lunch. Free lunch is over. Free lunch meant you could go to the beach for 2 years, you come back, and everything ran twice as fast. Because that's no longer the case, people have to think about new ways of doing computation. And this article does a nice job of explaining that those ways involve concurrency. So as a consequence of all this, what people are doing with all of those extra cores is all those extra transistors, is they're making more cores on the same chipset, and those cores, of course, can run in parallel. So you're basically getting a multiprocessor on a chip. And it's gotten to the point now where it's getting hard to buy a single core device, right? So obviously a server class machine is multi-core. Most laptops today are multi-core. Increasing numbers of phones and tablets are multi-core. It's just the way things are, right? And you can read some really interesting discussion about this, talking about the move from single core to multi-core and why multi-core isn't the panacea people would like it to be. And there's a variety of reasons it's not the panacea. The most obvious one is most people don't know how to program concurrent applications, so they don't really have the ability to take advantage of all those cores. So that's the real issue there. So that's, of course, going to motivate our focus on writing concurrent software, because if you can write concurrent software well, then you can start to take advantage of all these hardware resources that you've got. You have this abundance of resources, but you don't know how to take advantage of it. It'd be kind of like, I don't know if you watch The Walking Dead. It'd be like on The Walking Dead, you come upon an unlooted store full of canned food, and you don't have a can opener, right? So what are you going to do now? You've got all these resources, but you can't find a way to take advantage of them. So there's also other advances that have taken place over the past decade or so, and that is in the software and the infrastructure layers. And so most modern operating systems and virtual machines now have built-in support to take advantage of the multi-cores. So if you take a look at the Wikipedia article on multi-threading, you'll learn more about threads. We're going to talk a lot about threads in this course. We'll talk even more about threads in CS 282. We'll talk enough about threads so you can do your assignments, but you'll see that one of the cool things about Android is it kind of shields you from having to have a lot of knowledge of what threads do and how they work. So basically out there in the world, you've got things like Windows and POSIX, which is Linux, and Solaris and other Unix-based operating systems, VxWorks, Java Virtual Machine, et cetera. Those all take advantage of multi-core processors. And then there's also multi-threaded middleware. So middleware are layers of software that live on top of the operating system, but underneath any specific application. So of course, Android has got a lot of middleware in it. Things like web servers are middleware. Spring, which is sort of a container environment for web servers for running servlets and higher level cloud processing infrastructure. .NET, DDS, Corba. We've worked on something for years called ACE. These are all examples of multi-threaded middleware. And there's all kinds of cool stuff that's gone on over the many decades to make middleware and operating systems work better with concurrency. So the long and the short of it is, if you really want to be able to take advantage of all this improvement in infrastructure, where infrastructure is both hardware and software, you've got to be knowledgeable about concurrency. And depending on how much you want to learn about it or what kind of systems you're working on, you may need to learn a little bit about concurrency or a lot about concurrency. And it largely comes down to how important is it for you to be able to take full advantage of the underlying hardware. So there's some other reasons that we want to be able to use concurrency. So the main ones I've talked about so far were to leverage advances in infrastructure. But there's also some other reasons having to do with improving software quality attributes. These are things that make software better and do its job in a more effective way. So we'll talk about a couple of those. One, of course, is increasing performance, right? So that's That's an obvious thing. You'd like your applications to run faster, and you can do that by having things run in parallel. You'd also sometimes, and we'll talk more about this in a second, you'd also like to be able to improve responsiveness. Improving responsiveness and making things run faster may not be the same thing. You may take the same amount of time to get something done. You might even take longer. But if you appear to be responsive, people may be happier than if you made them wait on something. And we'll talk a bit more about that in a second. And the third motivation for using concurrency is to help simplify the structure of your software. And that turns out to be the most interesting and unusual reason, and we'll talk in greater detail about that. And that'll also kind of lead into the assignment 3 discussion. Improving software quality, hopefully people understand why that's important. It's important because people are increasingly using software, whether it be multi-threaded or not, for a growing number of mission and life and safety critical applications. So before, when we were just using software for sort of mundane things like generating reports or, I don't know, doing PowerPoint presentations in class or whatever, right? Those things aren't really life critical or safety critical or mission critical. But nowadays we're increasingly using software for all kinds of things in terms of figuring out where you are, getting goods and services to where they need to be in a timely fashion, protecting the cyber infrastructure, protecting the physical infrastructure, doing business on the web. All those kinds of good things are examples of how software is now very pervasive and very important in everything we do. So let's talk a little bit about concurrency and some of the benefits very specifically. So let's talk about performance first. When we talk about this stuff, I'm going to give you some example applications that are not unlike what you're doing for assignment 3, but have a little bit of a different twist, just so it's not identical cut and paste code. The example here is one you've probably seen me talk about before. It's basically downloading images using various concurrency mechanisms. And the way this works is it uses different Android frameworks like the Hammer framework. By the way, does anybody know what the name of the Hammer is? Very good. And so we'll use this as an example to illustrate the key points. All right, so what is performance? Performance basically characterizes the amount of useful work that can be accomplished per unit time. And you can either diminish the response time or you can increase the amount of work that can be performed. So you can either do more work in the same amount of time, or you can do the work in less time, right? Those are sort of two dimensions of performance, and they're more or less the same issue, just different sides of the coin. This is obviously a huge motivation for using concurrency. It doesn't always work out this way, by the way. But you might want to be able to minimize response time when you interact with the users, maximize throughput when you do database queries or other kinds of computation. You might want to reduce power utilization, which is sometimes a trade-off between these other characteristics. And you might also want to make sure things are available. These are some of the reasons why these are some of the dimensions of good performance. And doing this right involves a deep understanding of trade-offs between different quality attributes, because you very rarely get everything the same time, right? So you can have things be fast, you can have things be secure, and or you can have things be reliable, but it's sometimes hard to get them all at the same time because they're trade-offs in the design space. And so we'll talk about a lot of those things. And I should also mention, sometimes you can make things go really fast, but unfortunately your software becomes much more complicated, so it may be full of bugs, right? So how can we accelerate performance? Well, the most obvious way to accelerate performance goes back to that slide a few minutes ago that talked about multi-core and Moore's law. And so what you want to be able to do is you want to be able to do parallel processing. You want to be able to do multiple things literally at the same time. So one thing you might want to be able to do is perform multiple computations simultaneously. Like if you were doing some kind of image processing algorithm, you might want to be able to do computations on different parts of the image. Or if you have a server that's servicing requests from multiple clients, you might want each request to run in parallel so that you can take advantage of the multi-core features of the system and the abilities of the network to multiplex the flow of information in a seamless concurrent way. This is particularly relevant for so-called embarrassingly parallel programs. So does anybody know what an embarrassingly parallel program is? So an embarrassingly parallel program is one that has little or no dependencies between the different computations that are being run. So everything can kind of run in parallel. Can anybody think of an embarrassingly parallel activity that you probably do every couple of weeks in your dorm or wherever you live? Laundry, exactly. Yes, laundry. Laundry is an embarrassingly parallel activity, right? Especially depending how messed up your clothes look. It could be very embarrassing. But what you do is you can go take a bunch of washing machines or dryers, and you take your giant load of laundry and you spread them out throughout the machines, and you put your quarters in or whatever you use, and you push start, and they all run. And there's really no dependencies, right? Whenever one of them is done, you can take that and stick it in the dryer, and all those things can run, and they don't really have to coordinate at all. So that's a good example, a good metaphor for embarrassingly parallel computations. There's also other kinds of computations where you take a big problem and you break it up into lots of small problems, and each of those problems can be solved independently and then merged back together. Does anybody know of a good example in the world of computing that uses this sort of divide and conquer like approach, which is sometimes called MapReduce? Merge sort algorithm, yeah, that's a good example. So merge sort, if you remember, probably studied merge sort in 201, I hope, or whatever equivalent was that you took. It takes a big array and it splits it up recursively into lots of smaller pieces, and then you can basically sort each of those pieces and then merge them back together. So that's a good example of a so-called MapReduce style algorithm. Anybody else think of anything else that's all the rage these days whenever you do things on the internet? So whenever you do a Google search, it typically takes this string and it sends it out to lots of different computers, and they all compute the search results, and then those results get merged back together and you get the results back. So that's a classic MapReduce kind of problem. Android has a variety of ways to enable parallelism. The most common way you use parallelism on Android is by overlapping computation and communication. So you can have, just like for the examples you're doing here, or maybe to think a little bit outside the box, because your current application doesn't really showcase this for assignment 3, but you could make it showcase it. Well, basically what happens is you're able to download a file while still being able to interact with the user interface. For example, you could conceivably cancel the download if you wanted to, or switch applications to something else. And that goes in concurrently. The downloading, the communication of the file goes concurrently with other computations you might want to perform. And that would become more clear if we were downloading multiple files at the same time and doing other kinds of things. So the ability to overlap computation and communication is very essential, and Android does a lot of that kind of stuff with various features it provides. As we'll see later on, there's something called the async task framework. Grad students have to do this for assignment number 3. Undergrads are free to do it. And it basically allows computations to run in a pool of threads, and those threads can block on communication or computation independently of each other. And if you have a multi-core processor, then all those things will be going in parallel. Even if you have a single core processor, then as we talked about a couple weeks ago, while one thread is blocked waiting for I/O to complete, other threads could be doing other I/O or other computations, and everything could run at the same time, or at least logically at the same time. The example we'll see here for the image processing application basically ends up having a pool of threads that could run in the background, and the activity would download the image, or the activity would have a single thread that you could use to trigger the downloading of images, and there could be a pool of threads that could actually do the processing in the background. So that's about performance. That's about trying to get things to happen in parallel so that you can take advantage of the physical support for enhancing multiple processing elements on your multi-core processor to run at the same time. So that's largely about performance. But there's also this issue of responsiveness. And we have to think about this one for a variety of reasons. One reason we have to think about responsiveness is that not every computing platform actually supports the latest and greatest hardware. So you might have some computing platforms that only have a single core. What a horrible, tragic thing that would be, right, if you had to be stuck with one of these old computing platforms like that. Even if you have multiple cores, there are still situations where you may not be able to take full advantage of those multiple cores all the time. And there's a number of different reasons for that. And let's talk through those. These are things that tend to show up in quizzes. So if you have questions, make sure you ask. So one reason why you might not be able to take full advantage of the multiple cores or parallelism in general is because there are certain constraints on code that prevents it from running simultaneously. And this is typically an issue with so-called legacy code. What is legacy code?
Super old code.
It's code that's been around for a while. might have been written before multi-core processors were common. And if that's the case, it almost certainly is not going to understand how to use concurrency, right? Because there weren't multiple threads, so it would just do one thing. So sometimes it's because the code is old. Other times it's because there are certain constraints people impose on their legacy code for a variety of different reasons. For example, user interface toolkits, like all the programming stuff you see in Android or iOS that interacts with the users, the buttons and the menus and the dialogues and the widgets and the text boxes and so on. Those are all things that are deliberately meant to run only in the main thread of control. And you might want to take a look here and see why that is. Does anybody know why they have those constraints? What's the reason why legacy, or basically any toolkit that does user interfaces, only lets there be one thread of control that does that processing? So there's a couple reasons. Reason number one, most application developers don't understand concurrent programming. So if you allowed them to start using concurrency, they would probably get it wrong. That's number one reason. And number two reason is, when you start using concurrency, when you start allowing it, you have to put certain types of protections in your code to keep things from happening at the same time you don't want to happen at the same time. Those are called race conditions. And that requires adding locks all over the place. And so oftentimes, if you're not careful, when you take legacy code especially, but any kind of code, and you make it enabled to be run in multiple cores and multiple threads, the overhead actually goes up if you're not careful, because you have to put locks all over the place. And so you can actually make your code slower, even though you've got more concurrency and more processing resources, because it's spending all of its time waiting on things. And you probably had this experience in your own life. If you haven't had it yet, you'll probably have it by the time you take the software engineering projects course, the CS 279 course. In CS 279, you learn a couple of important things. You learn how to work in groups, you learn how to work on bigger projects, and you learn how teams can often slow you down, because you'll end up depending on somebody who doesn't get their job done at the right time, and the whole project becomes late. And you'll eventually think to yourself, especially if you're really good at programming, I should have just done the whole thing myself and not tried to work as a team, because we got all messed up and we had to synchronize and coordinate our activity, and that slowed us down. And that's very true in multi-threading as it is in everyday life. So user interface toolkits are often intentionally not thread safe. It's important to understand some reasons why. And Android certainly has that characteristic, and you can read this link to find out more about the constraints it has. There's another reason why we often can't take full advantage of multi-cores or parallelism also. And this is something that's called Amdahl's law. Does anybody know what Amdahl's law says? Yeah?
So you can only speed up like a certain part of the processor and
So to rephrase what you said, what it basically says is you can only, it says the speed up from parallelism is a function, I mean, it's really sort of an obvious statement. The speed up from parallelism is only a function of things you can actually run in parallel, right? So if you have an algorithm and 80% of the time that algorithm has to be sequential because of waiting for dependencies on data or other things, it's not going to benefit from running on a parallel processor. That particular instance might. Now you might be able to replicate the thing so you can have multiple algorithms running in parallel. But a given algorithm is only going to benefit from parallelism to the extent that it has code that can run in parallel. And so basically this says the speed up of a program using multiple processors in parallel computing is limited by the time needed for the sequential fraction of the program that can't run in parallel. And once again, you often find this in everyday life, right? There's certain things that you'll sometimes do, especially as you move on in your career and you start to manage groups of people. There's often a trade-off between delegating something to someone or someones to do the work versus just doing the work yourself. And so if you end up with something where you're waiting for everybody, then you may not really get a speed up from having lots of people do it, because you'll spend all your time synchronizing and coordinating and not actually doing the work. So that's what's called Amdahl's law, and you can read more about that here. So given these conditions, right, given the fact that you may want to run certain code in one thread or a bunch of functionality in one thread, or you have to run it in one thread, and this dimension of Amdahl's law, concurrency can still be a win, because it can often give people the perception that things are more responsive, even if they don't run faster. And so responsiveness is this ility, this dimension we're talking about. So one simple example that we see in Android, and we'll talk more about this in a second, is that Android is set up so that while you're doing something in the background that might require a lot of I/O or computation, you can still keep the foreground thread free to be responsive to the user, either to switch over to do something else or to cancel a long-running operation or to do some other operation, start some other operation. So you don't end up in this somewhat embarrassing situation where you've got a block for a long period of time while something's going on in the background and the user interface is not responsive. Anybody who's ever programmed with older versions of Mac OS or older versions of Windows knows the dreaded hourglass you used to get. You guys probably haven't seen this in a long time, but back in the day, when you did some long-running job that involved downloading a file or whatnot, you get a little hourglass figure, which is why there's an hourglass up here. And that meant I'm doing something in the background, I'll get back to allowing foreground input when the background thing is done. And that was very annoying because it wasn't responsive, right? Even if it took a while to download the files, even if it took the same amount of time to download the file, if you could do something else in the meantime, you often feel more at ease. You feel like you're being more productive, right? So that's what responsiveness is all about. And Android provides a bunch of concurrency frameworks that define features and programming idioms for ensuring responsiveness. And that's, of course, that whole discussion we have about application not responding dialogue that gets popped up when things take more than 3 to 5 seconds to run. And that's why you have to understand concurrency in order to do assignment number 3. Yeah?
So in Android, does the user interface thread always have priority over any background threads that you've done?
It doesn't necessarily have priority, but if you use async task, for example, by default, it'll give the foreground thread priority over the background threads that run. But that's just because of the way that that works. You could spawn your own threads and give them even higher priority if you wanted to. It might be crazy to do that. If you made a background thread that had really high priority, your foreground thread might never get a chance to run, even though your user interface is sitting there looking like it should be responsive. It wouldn't be. So typically what you would do is you would either give the background threads the same priority as the foreground thread or lower priority. And if you give them the same priority, then the system will time slice between them. And so your foreground thread will get periodic chance to run. Obviously, if you give it a lower priority, then as long as you're typing stuff to the foreground thread, the background threads won't run. But usually, human interaction is a lot slower than computation that can run in a background. So even if you're typing, the background threads will get a periodic chance to run because you aren't typing fast enough to take up all the CPU power. Yeah?
Does the async task spawn a thread that runs on the same core?
The async task, and we'll look at this in much greater detail later, but to answer your question shortly, the async task has a pool of threads, and there's various ways to configure it. So what I'm about to say has several answers depending on how you configure it. But let's assume we have a pool of threads configured with the async task. When you do something, when you execute an async task, it takes whatever you want it to do and it passes it as a message to one of the threads in the pool of threads, and those guys go ahead and run. And how those threads actually get mapped onto the underlying core is a function of the Java thread scheduler, it's a function of the Linux scheduler, but most likely it'll run on another core, right? There's various ways you could kind of nail it down if you so chose to have it run on a specific core, but that would be unusual. You'd have to do extra work. So usually an async task background thread will run on some other core that's not being used at that point. And the UI thread would probably run on a different core that wasn't being in use. But that's really sort of more of a system implementation decision or configuration decision. So the Android UI thread can interact responsively with a user while other threads in the background or async tasks, which ultimately use threads, can be doing longer running computations and or communication in background threads. And that, of course, is exactly what you need to have in assignment number 3 for your download image activity. The download image activity that you're going to write is going to need to have something going on in the background, because if it doesn't, it'll be running in the same thread that the UI thread is in, and when you try to download the file, you'll get some weird error, and you'll be like, what the heck happened? What was the exception that we were getting? I/O exception or something like that?
It was a network exception.
A network exception. I think the exception is basically saying you can't make network calls from the main thread. That's essentially what it was doing. Okay, so those are 2 reasons so far. Good things to know, 2 reasons. Performance, in other words, making things run faster, and responsiveness, which is giving the appearance of interacting with the user more responsively, whether or not the actual performance is any higher or not. Another good example, by the way, of responsiveness would be an ATM machine. When you go to an ATM machine, you put your card in, and then you enter in your PIN number, and then they give you a menu, and you select the function you want, blah, 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 and it walks you through a bunch of steps, and then you want to either deposit something or extract some funds or whatever. And while all that interaction is taking place, some computation is going off in the background, checking to see if that's the right PIN, checking to see if you have the money in your account, all those other good things, whether you've stolen the card, that kind of stuff. And in some sense, the menus that you're led through are just kind of there to give the system a chance to do that longer running computation in the background to figure out if you have access to the funds you're trying to get to. So that way you appear to be doing something useful, but there's also something taking place in the background. It would be really annoying if you just had to sit there, with the UI frozen at the ATM while it was doing all that computation in the background. All right, the third and final topic we're going to discuss here, hopefully we'll get through this, is simplifying program structure with concurrency. And this is a little bit surprising. So concurrency, even though concurrency can be harder to program, it can also help to overcome certain drawbacks with poorly structured software that looks like spaghetti code. So this is the icon that I use throughout the slides for spaghetti code, and we don't want spaghetti code. So before we had multi-threading, people wrote programs, user interface-based programs primarily, that use some kind of an event loop. You can read here about event-driven programming and event loops and so on. And in these environments, you would have one thread and an event loop, and that event loop was responsible, that thread was responsible for putting things onto the event loop and taking stuff off the event loop. And it was all done in one thread of control. And this was difficult because it made it hard to avoid blocking, and or it required your software to be split in time and space between starting an operation and then completing the operation with the results that came back. So the challenge here is that single-threaded programs that are event-driven tend to be somewhat obscured in time and space. So one of the consequences was that you couldn't do a blocking call, because if you did a blocking call in a single-threaded program, then the entire program would halt while that call blocked, and that might make the thing be unresponsive, right? That's where you get the little hourglass that says this isn't going fast enough, you're going to have to just sit there and wait, which is always very annoying. The way that you do long duration operations in a single-threaded event loop type model is you post messages into the event loop's message queue saying, I want you to download something for me asynchronously. And somehow magically that would take place using all kinds of crazy mechanisms that were done by the operating system kernel but not exposed to the application level per se. So you put a message on the queue saying download me a file or upload a file or whatever you want to do. And then when that thing was finished at some point later, the message would come back and say you're done. But the problem was that was decoupled in time and space. The piece of the code that put that request into the queue is literally in a different space in the code that the part of the code that handles the results when it comes back. So that would literally be in different parts of the code. And of course it occurs at different times because you do the operation, you request the operation, and then later you get the result back. So there's a decoupling between operation invocation and operation completion in time and space. And there's a bunch of patterns for programming like this, but they require additional understanding of asynchrony and callbacks and completion handlers and that kind of good stuff. So one way to use multi-threading, which is not necessarily to make it faster, although it probably will make it more responsive or give the appearance of being more responsive, is to use multi-threading to structure your software. And so we're going to talk about this first, and later we'll come back in the course and talk about other ways to do this. But for right now, we're going to talk about multi-threading. And instead of doing this crazy event loop with asynchronous operations and splitting invocations from completions, what you instead do is you have multiple threads and you allow the long duration operations to block synchronously. And you'll recall we talked about synchronous blocking last time, where I used the phone call as an example where you block waiting for someone to pick up the call. And this allows a more coordinated approach to control flow because you can have these threads blocking. And as we'll see in a second, it helps to simplify application structure because now the operations are more cohesive in time and space because they can block at the point of the call, and when the call is done, it simply returns and you continue on your merry way. And we'll talk about async tasks in more detail. So using async tasks as an example, Android's async task model, which is what the grad students are doing for assignment 3, the long duration operations can run in these background threads, and they can afford to block because they're not blocking or interrupting or disrupting the flow of control that the user interface thread is doing in the main thread, the UI thread, and where the short duration operations are running. And as a result, your code is not as spaghetti laden. And you'll see that if you do the async task framework, you'll see your code is very clear once you understand how it works, and it's real nice and cool. So you can use this to do all kinds of stuff where you need background tasks that run separately from the UI threads. There are a whole pile of patterns we'll talk about if we have time later in the course. We'll certainly cover them in 282 later. All right, good. This is right on time. So what I'd like to do next is I'm going to look at a little bit of the code in this image downloading application and illustrate, by walking through a little bit of code, a little code fragment, how multi-threading enables the solution to be more cohesive in time and space. And this will then give you some hints about how to structure portions of your assignment number 3. So this particular application is going to download images from remote server or servers and display them on the phone. And you can actually download the phone. I mean, you can download the application here to see what it does. It's pretty cool. So you basically grab something from the web, and then it uses a couple of different ways to run things concurrently. We're going to see it's going to use it'll use a Java thread, and it'll also use the Android Hammer framework. And we'll see how those two things work together very nicely. So if you recall, with a Java thread, you define a runnable. And the runnable specifies what the thread should do. And you can go here and learn more about threads and runnables and so on. And here's an example. We'll look at this in more detail in a second. But you're going to create a runnable that has a method called run, and that's the code that you want to run in the background. And then you'll go ahead and use the Java thread class, which is described here, to start the thread. Oops. You'll go ahead and use this thing to start the thread with the runnable. So that'll then start up a thread which will run in the background doing whatever this thing says. And we'll look at what this thing is in a second. Now, to understand this piece of code, you have to know ever so much about Java threads, which aren't very complicated, but you need to learn about them. And we'll talk more about these things. You can either watch these videos online, or maybe we'll have some chance to cover them. We'll certainly cover them in 282. We're also going to do something else. So the Java thread is going to be used to run something in the background. And then we're going to use the Android Hammer framework to get the result of the computation that's running concurrently in the background to download the image and get it to display the image back in the user interface thread. And we're going to use the Android Hammer framework to do that. And you can learn more about the Hammer framework here. And what this will do is basically download the thing in the background and then give it back to the main thread for displaying. So let's take a look at the code. As you'll see here, the code is very concise. Yes, Win?
So unless you specify run on your thread, you can just do a start, it'll automatically send it to the background.
So you can, when you do start on the thread, it runs in the background, which is fine. You can download the image, as we'll see here. The tricky part is how do you get the results of the downloaded image back in a position you can display that image in the UI thread, because you can't display the image from the background thread, because any operation that involves user-facing control can't run in the background. It has to run in the foreground. That's one of the constraints of the Android system, much like any UI system these days. OK, so here's the piece of code we're going to look at. Now, first thing you want to see when you look at this code is it's very cohesive in time and space. And you'll see why in a second. So when we click run runnable on the GUI, that creates a call to this method here. And this method is what handles that button press. And it creates a runnable, as you can see here. And it goes ahead and starts the thread with that runnable as the parameter. So it goes ahead and starts the thread. And now that's going to run in the background. And when it runs in the background, the run method gets called. And you'll see what it does is it synchronously downloads the image. So that's similar to your code that you have. And once it's done downloading the image in the background, now it's got to get the result back to the foreground. Now your program is a little different from this, but the basic idea is still there. So what we can do here is we can create another runnable, which is basically a command. And inside of this command, we're going to basically have a run method. And this run method is going to run the command in the context of the user interface thread. So what we do is we make this command that has a run method, and this run method is going to run on the user interface thread. And the reason we know it's going to run on the user interface thread is because it says run on UI thread. So we give it a runnable command, and it goes ahead and it sticks that command, that runnable command, into a message queue that the main thread of control, the UI thread in Android, will pull out at some point in the not too distant future, and it'll call back on its run method, and that will cause it to set the bitmap that we downloaded to be the view that we want to have up here. So these methods run in different threads. They do not run in the same thread. OK, so is there any question about that? Yeah?
So there's no need to like explicitly restart that UI runnable because that when UI thread.
The UI thread exists already. You don't have to start it yourself. It's part of the Android infrastructure. And it just sits there waiting for events to pop out of its event queue, its message queue, and then it does stuff with them. And in this case, it'll call the run method back. So this thing will get run in the right context, in the UI thread context. So the cool thing about this is that these things run in different threads, but it's very cohesive. So in the original approach that used event-driven programming, what you would see is that these messages would be decoupled in time and space. They would literally exist in different parts of the code, and you'd have to match them up in your head somehow. Whereas in contrast, in this approach, notice how cohesive things are, right? We see one piece of code. This is cohesive in space, right? It's right next to each other. They're literally in the same couple lines of code. And they're also cohesive in time because this call will block. And so until this call returns, this thread will be blocked. And when the call does return, the thread wakes up again and continues its processing. Yeah?
You called or referred to one of your members from the original class.
Yeah, great question.
Since we are in a subclass or subclass, or can we call actually a method instead?
So I'm not exactly sure what you mean, but let me.
Can we call a protected method that was defined in the main?
Oh, yeah, you could do that, yes. In this particular case, notice how we make bitmap final, and that allows us to be able to use this bitmap in a different thread of control. Hey, Danny. You can use this bitmap object in a different thread of control because it's been made final, which means it's not going to change. And this is sometimes known as a closure. We won't go into a lot of detail about what closures are right now, but they're basically little commands that can take the context in which they execute, which might include sort of non-local variables and so on, and access them in a different context where they're executed. OK, so at this point, you should have a pretty good idea of how to do assignment number 3. That was sort of the missing piece we hadn't covered so far. In the remaining minute or two before the quiz, any questions about any of this stuff? Yes, sir.
So the longer running processes that have to do with background, the process of sort of have one application and one UI thread, like all that is happening that thread. Well, when you separate background threads, is there a specific one, or is it more global?
Yeah, great question. So the question is, if you have more than one thread, where do those threads run? And you'll find out later there's a bunch of different answers to that question. Let me keep a simple answer for now. For the activity-based solutions we've been looking at up to this point, those background threads run either in a thread you explicitly spawn, as we did here, right? If you take a look here, we explicitly start this thread, and so that runs in the background. And when it's done, it'll just evaporate. Or you can run it in a pool of threads, which you probably didn't spawn. So people who do the async task version of assignment number 3 will see that there's a pool of threads that they didn't actually create, and that's where the computations take place. If you do the Hammer framework version, you are responsible for creating the thread. So it really depends on whether you use the Hammer framework or if you use the async task framework, where the threads come from. Now later, we'll see that there's a whole pile of other stuff you can use for running services in the background, but that'll come later in the class. Good question. Other questions? Win.
How would I spawn a new UI thread? Or would I
You don't spawn a new UI thread. There's only one. It's like who was the guy? Was it Highlander? There can be only one, right? You know.
Wait, so I would just make a new activity?
No, making a new activity doesn't matter. There's one UI thread that exists in an application, whether or not you create activities or not. Yes? No, it was. I think it was the High. Who? It was the Highlander. Okay, yeah, great movie. Yeah.
C++ doesn't allow you to define the nested function in the function. Is that right?
C++. Are you asking does C++ allow nested functions?
Yeah.
Well, not really, but you can have functors, which are basically the same thing in C++.
Java just allows it.
Well, Java doesn't really allow nested functions either. What we're doing here is we're making anonymous inner classes. We're making instances of anonymous inner classes. Another question?
So with that said, like there, looks like on the UI thread starts after download image and
Yeah, so the way to read this is that this run method here gets called first when we start the thread. It downloads the image synchronously. If you were to look at the code, it was just like the code that you have in your download utils. And after this is done, then a new runnable is created, which is a closure or a command that has access to this bitmap here. And that new command is passed to the UI thread. So this gets run first, followed by that. But this thing just puts a message in a message queue. And then later, once that message queue comes up through the UI thread's event loop, then it'll call the run method back. The event loop code in Android automatically calls the run method back, which sets the bitmap to be the image that's displayed. That's a good thing to look at the Android documentation to really get your head around. We'll cover it later in the course, of course, in much more detail. Danny?
One question: If you don't, do you try to run IB.set bitmap outside of a run on UI thread? Would it throw an exception, or would it just be undefined behavior?
So what are you trying to do?
If you try to do like something in UI, like IB.set bitmap, but outside of a run on UI thread, so like in the actual.
Oh, yeah. If you make calls to UI threads outside of the UI thread, then it's probably going to throw an exception because it's probably checking to see where those methods are called from. You're probably checking to see if the methods are called in the UI thread. Even if it doesn't throw an exception, it's a bad idea because it's really undefined behavior. And so you'll be surprised in an unpleasant way at some point in the future if you do that. You'll also end up with race conditions too, which is even worse.